when after doing the work, another form can creating is the kinetic energy, in which cases is KE equal to 1.5 mv squared. Now, in these cases, involving another stuff is all this energy per se can be used to do the work. Can be used to do the work. Again, or this energy can be dissipated to do the motion. In which case, when you're doing the motion, you need kinetic energy, 1.5 mv squared. Or you need to do what we call lifting up against gravity. Yeah, in that cases, they're kind of called mgh. That related with potential energy. And on the top of it, when you're doing this, it can against what we call friction. Then friction, what does the friction do? Friction will do the work. Friction can do the work. Can do the work. But this work is wasteful work. Very wasteful work. That means is not very useful work, the friction. So work can be stored. That means energy stored. In terms of potential energy, in terms of kinetic energy, but at the same time it can produce motion and can move the object up. That's in this case is number 53, chapter 6. Number 43. Number 43, it has a potential energy stored in the spring. And when you release it, it's creating motion, in which cases is kinetic energy. At the same time, it needs to do some work, in which cases this is another thing of work, to move the ball higher. So the ball is moving some place from here to here. That needs energy. That type of energy from the energy converting to work to make this go higher. And then in the future, there's a friction. So when you move here, there's some kind of friction is involved to fight against that. In these cases, it does not including in here. Now the same thing with the example 6.5. 6.5 has the same situation. 6.5 is here is the spring. Somebody move these things up in here. When you move this up here, it's doing the work. Wherever you move, when you move up to here, in reference here, you do getting some work. So, but this work can be released in terms of potential energy. So it will compress it down. So compress it down. So in these cases, that is a delta x. Then they compress the potential energy down, in which case equal to 1.5 kx squared. Okay, so at the same time, this move down certain distance. Move down certain distance. So this is one distance, and here is one distance. So this is the bottom line of it. So after we learn about this, then potential energy means that the energy is in position, how high you were, and so forth. And then the other chapter on that is chapter 8. Chapter 8. There's some place between chapter 7 and chapter 8 introduce a very important situation. It's called conservation of energy. Conservation of energy. In that case, is related on page 197. That means the energy cannot be destroyed, but it can transfer between potential energy, or kinetic energy, or work, including friction. So now it's up to you second guess where the test comes from. We only give you 4 questions. Okay, among these 6 questions or 4 questions? 6 questions, right? 6 questions, I eliminate 2, right? So only for you to study for chapter 6. Among 4 questions, and you're going to pick 2 for the midterm for the chapter 6. Okay, you understand now?
The question again?
You're picking 2 out of 4 tests.
Chapter 2, chapter 6?
Chapter 6, yeah.
Yeah, 1 out of 4.
Oh, 1 of them. Okay.
Okay? So you should have enough time to study for at least chapter 6.
Yeah.
Okay, now we move on to review on chapter 4. Reviewing on chapter 4 and chapter 5 at the same time. Now, chapter 5 has no homework. The only homework we have on the chapter 5 is I want you to study the examples. Study the examples. Okay. Now we would like to compare what we learned in chapter 4, what we learned in chapter 5. Chapter 4, we're talking about Newton's second law. Okay. Chapter 5 is Newton's second law. Second law. On the whole chapter, he is talking summation of F is equal to MA. Simple case. How simple? There's no resistance, force, or no friction. Idealistic cases. There's no friction. Is everything in Newton's second law in chapter 5. So ladies and gentlemen, make a mistake. Chapter 4. On the chapter 4, all is assumed. Assume 2 things. Assume is smooth surface. Okay? And then another thing, we always assume no friction. Means no resistant force. That's from the English point of view. If that is the case, if you want to find out the association of the first thing you have to find out what is the force. That's why in chapter 4, have to find out that what is the net force. There's so many forces acting. What is the resultant force to give you some desired motion? Okay, so In these cases, the number one thing you have to do, you have to draw the diagram. Find out where the force come from. Find out where the force come from. This is very crucial for you to solving this problem. We like to show you one problem. Is a relationship with that. One of the problem we have, in which cases you pick all the physics book, they will must have some kind of problem like that. One problem they have is something like the slide. This slide is always occur in any physics book you pick. Now this one they're talking about slide. In these cases they talking about snow. So put it this way, in the snow. All the snow is piled up here, and a slab is on the top of it, a slab. So that means some kind of kit is on the top. I didn't draw this. This is, like to say, is example 4.3. Example 4.3. They said snow. What it means is snow. When you have a snow surface, it indicates smooth surface. In this case, they like to using that. It says a child on the slab is released on a frictional heel of an ankle fader. Sometimes they say on the snow heel. Determine the association of the slab after its release. So this is an ankle fader. Okay, so now from this type of problem, no friction, so that you have to determine